2, moving. Electrons can actually move around quite a lot within an atom, and they can also leave one atom and join another one, or be shared with another atom. So electrons are a little bit more interesting than protons and neutrons, and they're also much harder to understand. So most of the struggle of quantum mechanics and some of the more difficult physical and chemical sciences really break down to the difficulty of electrons. So part of what they're doing a lot of the time is electrons, I'm sorry, that's an error, atoms want to have a full valence shell. So what this means is that outside shell that we talked about in the last lesson, that outside ring, pretty much every atom wants that to have 8 electrons in it. The only exception to this is very small atoms only have the first ring, and that's actually full with 2. So this actually means just this full outer ring that basically makes an atom feel happy. For this to happen, atoms tend to gain or lose electrons. Now, we're not going to get into a lot of the details of this because this is truly bonding, which is a later unit for us. But in order to understand a lot of things that are happening in chemistry, we have to understand this 8 valence electron thing and this desire that atoms have to get these 8 valence electrons. This can be done by gaining or losing electrons, which will form something called ions. Ions are no longer atoms. Remember, atoms have to be neutral. So in order to be considered an atom, you're neutral. An ion is actually something that used to be an atom but became charged because of gained or lost electrons. It's extremely important to remember and understand. Protons are never gained or lost. So if something's positive, it's not because it gained protons. It's actually because it lost electrons. So the number of protons has to stay the same within an atom. We're going to draw something today called Bohr diagrams. These are a little more involved than the Lewis dot structures that we drew in the last lesson. They give us a different set of information. They also show us those bonding electrons, but they show us the kind of a picture of the electron configuration as a whole. So we got to find the atom that we want to draw on the periodic table. So we're going to do chlorine. I like to draw a little circle for the nucleus, and I draw the necessary rings that I'm going to need. Looking at my electron configuration right here, I'm going to have 3 PELs. So I drew 3 rings, and I'm going to fill electrons in. There's a couple ways you can do this. You can use little dots. I like to use kind of little lines. So my first ring is going to have 2 electrons in it. So you could do this. I do like to pair electrons. They do actually exist in pairs. So you could draw 2 little dots like that. If you don't like dots, you can draw 2 little lines like that. That kind of is a quick and easy way to do these. My second ring should have 8 electrons. Again, I like them paired. 1, 2, 3, 4, 5, 6, 7, 8. And my outermost ring is going to have 7. 1, 2, 3, 4, 5, 6, 7. So electrons really are paired, which is why I'm showing them this way. Also, this will help you to kind of keep track of how many electrons you have. If you jumble them all up on one side, you got a lot of counting on your hands, whereas visually you can pretty quickly count these. If you look at magnesium, so if you find magnesium's configuration, 282, we've got 3 rings again, nucleus in the center, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2. These are pretty straightforward. They're not hard to do. What's important is just to remember the difference between a Bohr or a Lewis dot diagram that can be a little bit confusing sometimes. Now, these will help us to determine the charge that an ion will have. So we have 2 types of ions, cations and anions. Cations are positive ions, and we're going to talk on this slide about how those form. So if we drew first a Bohr diagram for sodium, whose configuration is 281. Now this visually lets us see, hey, if we want 8 on our outside ring, what could sodium do? So sodium has 2 options. It can either gain or lose electrons. In order to have this outside ring have 8 electrons on it, it would need to gain 7. That's hard, okay? In order to have an outside ring with 8 electrons on it, another thing that could happen is this 1 electron could get lost. That whole ring would then be gone. Notice this layer below it to do is sodium's going to lose one electron. So when this happens, we're now going to have 2, 8, and this outside ring pieces out completely. Now that space is still there, like an electron could end up there at some point, but we don't have to really consider it right now because there's no electrons on it. So what that actually did for me is it formed this thing called an ion, or a charged atom, where I now have sodium feeling like it has 8 valence electrons. Now we're going to calculate the net charge, and this is actually something you can look up on your periodic table, and down the road you will, but I want you to really understand where this net charge comes from. To figure out the charge that an atom or an ion has, we're going to look first at our number of protons. So if you look at sodium, sodium has 11 protons, and those are positive. I'm not even going to put a positive sign. Just say, hey, 11 protons. Now, my sodium atom had 11 electrons. My sodium ion has 2, 4, 6, 8, 10 electrons. So I'm going to subtract from my protons my electrons. Because electrons are negative, so I'm subtracting it. So I'm going to do 11 minus 10, which gives me positive 1. If you look at sodium on the periodic table, you're going to notice we have this thing called an oxidation state in the upper right-hand corner. Sodium's oxidation state is +1. This is actually the charge that we expect sodium to form as an ion. A cation is a word for a positive ion. So this is a positive ion, we can call it a cation. Now, small atoms feel a bit different. So if we actually look at beryllium, I just want to draw your attention to this. It's not super complicated, but we've got the configuration 2, 2. So what's confusing to this is, or confusing about this, is that beryllium's never going to have 8 valence electrons, or 8 electrons on its outside ring. It's never going to have 8 electrons at all. It just doesn't have the protons it needs to hold on to that many electrons. So what's actually going to happen with beryllium, this ring right here is not full with 2 electrons, but this ring is full with 2 electrons. So what beryllium's actually going to do, it's going to lose those 2 valence electrons. It's going to lose these guys up here, and actually just have only 2 electrons right here. And this, oops, those are attached. This outside ring, this outside ring is going to leave, just like in the last one I looked at. And now we just have the nucleus and those 2 electrons. So this isn't really that weird, except you just have to remember that first ring is actually full with 2. So it's full and happy with 2 on it. We don't need any electrons here. We're going to calculate our charge the same way. Beryllium's atomic number is 4. It's got 4 protons. My beryllium ion has 2 electrons. 4 minus 2 is positive 2. Look at your periodic table and make sure that it agrees with the charge given for beryllium. So we just talked about our cations. Cations, again, as I've told you, are positive ions. They form when electrons are lost. And that can be very weird. How am I positive if I lost something? Remember, you lost something negative. When you subtract the negative, you get a positive. Elements that form cations tend to be found on the left side of the periodic table. So the examples that we just looked at, they're all from the left side of the table. Those are metals. You don't have to write this down, but just a point to know is that you have to be able to draw dot structures and Bohr diagrams for cations. So that's what we're going to do right now. So first thing we're going to do, we're going to look at potassium. Potassium's electron configuration is 2, 8, 8, 1. When potassium is trying to get 8 in its valence shell, what it's going to do is lose this guy right here. So my configuration for my cation is 2, 8, 8. Now we did dot structures in our last lesson. Dot structures, remember, are different from Bohr diagrams. So our dot structure is showing just the valence electron. So my atom right here had that 1 valence electron, so my K gets 1 dot. And here's what's weird. When a cation forms, you sort of have this ghost of electrons cast right there. There was an electron there. Our dot structure needs to still show that same valence shell. The reason for this is because dot structures are showing bonding electrons. That electron actually lost because it's bonding with somebody else. So we're now going to show our K, and it might be tempting to draw 8 electrons, but don't, because we really have no electrons there anymore. There's nothing there. It's almost like that's 2880. So we're not going to show any electrons because we lost our 1 electron. But we do have to tell people we lost it. So in order to tell people we lost an electron, we say +1. And again, if you're kind of like, where did you get that +1 from? Look at potassium's atomic number, which is 19. How many electrons does our cation have? 2 plus 8 plus 8 is 18, so I'm going to subtract 18, and that gives me +1. The other place that you can find it is if you look at your periodic table, that top corner has that +1, which should agree with a calculated net charge. So we're going to do 2 more. We're going to do magnesium. We're going to do aluminum. Magnesium is 2882. Or I'm sorry, just 282. My configuration for my cation, I'm losing those 2 electrons. This is just going to become 28. Now my dot structure for my atom includes those 2 electrons that were in my valence shell there. For my cation, I'm going to drop those 2 electrons, but I have to tell people, if we lost 2 electrons, losing electrons makes us positive, 2 of them makes the number 2. Some people like to show these in brackets, so if you want to do this, that's totally cool. If you don't feel like it, don't worry about it. Last note, we got to fill in our charge there. Remember that +2 should agree with magnesium's charge on the periodic table. So you check it out, look in that top corner, you should see a +2 there. So aluminum is 283. Aluminum likes to lose 3 electrons. My neutral atom is showing those 3 valence electrons. My ion, or my cation, is showing that those have been lost. Losing is positive, and I lost 3. And that agrees with what I have on the periodic table. So most of the time you don't have to think too much about this because you can always reference your periodic table. Anions are the opposite of cations. So an ion is charged. It can be positive or negative. A cation is positive. An anion is negative. Anions formed when electrons are gained. So cations formed by loss, anions by gain. And these elements are found on the right side of the periodic table. So they tend to be the nonmetals. If you be able to do the same stuff with these that you did the other one, again, you don't need to write this down, but these are the things that you need to be able to do. So we're going to start by drawing a Bohr diagram for chlorine. Chlorine's configuration is 287. Again, exact placement doesn't matter, but I like them kind of paired like that. To get 8 on the outside, chlorine can either lose all 7 of these, and then that inner ring will be 8, or it can just gain 1. Electrons aren't like money. They're just as easy to gain as they are to lose. So what chlorine's going to do is it's going to gain 1 electron. So if we want to redraw this, we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 2 are 8. And we used to only have 7 on the outside ring. Now we're going to have 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 on that outside ring. So let's look at our net charge here. If we look at our net charge, we're going to look at our number of protons, which is 17. We count our electrons in our ion. We have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we're going to do 17 minus 18 to give us -1. I noted BR here. The only reason that I really noted this, oh, and by the way, that -1 should match that first charge on chlorine. There's some other ones there. There's some weird stuff going on, but for right now, we're just using the first charge listed. I just mentioned this because its configuration is 2, 8, 18, 7. Some kids are like, what's going on with that? That's not an 8. But it doesn't really affect anything. Bromine is also going to gain 1 electron, and that will end up becoming an 8 when it's an ion. So it's noted as a weird exception, but it's really not. So we have to be able to draw dot structures for these. So we're going to look first at sulfur. So sulfur's configuration is 286. What sulfur is going to do, it's easiest for sulfur to just gain 2 rather than losing 6. Our atom that we started with should have had 6 dots. And our ion, because remember, we're always looking at this, our third ring for sulfur is our valence shell. So now our third ring has 8 electrons in it. So sulfur is actually going to have 8 electrons drawn in its dot structure. But it is important that we still tell people sulfur doesn't really own these electrons. Somebody gave them to them because they bonded. So we're going to write that we gained, which makes us negative, because we're gaining negative stuff. More electrons make you negative, and we gained 2 of them. If you look at sulfur on the periodic table, the very first charge listed is negative 2. So that works. I'm going to walk through nitrogen. Nitrogen's configuration is 2-5. So again, we'll just do this dot structure first quickly. We got our 5 dots right there. It's easiest for nitrogen to gain 3. So nitrogen's going to become 2-8. So nitrogen ends up, just like sulfur, looking like it has 8 dots. And therefore is a negative 3 charge. Negative because we're gaining, 3 because we gained 3. First charge listed for nitrogen, you'll notice, is negative 3. Again, a lot of people, especially with all these dots, like to use the brackets. It's totally up to you. What you're going to notice, your anions get 8 dots around them, and then they get that charge, that negative charge. Your cations have no dots, and they got that positive charge. Argon's a little bit weird, so I just want to take a quick look at it. Argon's configuration is 288. Argon doesn't form an ion. It's happy just the way it is. It's got 8 valence electrons. So argon does have a dot structure for its atomic configuration, but again, doesn't form an ion, and its oxidation state or its charge is considered 0 because it does not gain or lose electrons. Give a little ion review table. Take a minute to fill this in. Keep in mind that there are heavy exceptions to 8 is great. If you have really small atoms, I don't think I put any of them on here, but you can also have noble gases, which aren't going to do any formation of ions. So pause the video for a minute, try each of these, and then you can unpause it and check your answers in a minute. So we check these out for a minute. What you're going to notice is any of the ones that form negative ions end up with 8 dots around them as an ion. Any of the ones that are positive ions ended up with no dots. And you're always referencing the very first charge listed on your periodic table. When I wrote these as ions in the column all the way to the right, this is actually how you'll be writing ions through a lot of the year. We haven't really practiced it yet, but you just write the symbol and write the charge with it. So again, double check all of these and make sure that in your Lewis dot structure for your atom, it matches your valence electrons. So the number of dots here should match this. And keep in mind, I know sometimes this gets a little bit confusing with the positive ions. So you're always showing your third PEL for sulfur. For sodium, you should also be showing your third PEL because you initially had 3 PELs. So you actually kind of have 0 electrons there, which is why that positive ion ends up with a 0 there. We're going to stop there. We're going to do electron excitation separately.